Oscillating detectors is another term for regenerative detectors. In the 30s, they went wild, hog wild on this stuff. But there's a lot of good information here for people to understand the deep technical matters of this. Super regeneratives are covered again. You can see it breaks into oscillation. At this point, you can see it breaks into it stops, it breaks into it stops, and therefore you don't get the oscillations that you would get here and here, up there. And there's a lot of information on how you relate the quenching frequency to the carrier frequency. That's also a lot of Fourier analysis and that sort of thing to go into that. Now we go to Drake's Radio Encyclopedia. This is for the everyman to build. This is good. This tells you how to wind the coils and all this stuff. As you can see, we got regenerative detectors. This does the exact same explanation of it. And it goes with the effective regeneration, low regeneration, it's wide band, high regeneration, it's narrow band. You can see this is taking on a much smaller chunk of the bandwidth. Now you see this is one method of controlling the regeneration as we see here. This is basically a feedback oscillator. By rotating this coil, you're changing the coupling of the coil, and you get more or less by rotating this coil. That's the tickler coil, they call it. You have an actual little coil inside the other one that you can rotate. This is excellent because this allows you to maintain the potentials in the tube and control the amount of regeneration, so you control the point where the noise voltage just cuts off and saturates the tube. It makes the tube very nonlinear and is very sensitive to etheric functions. Now you see, they take another idea. Put a resistance in series with the feedback winding. Make that resistance bigger, you get less feedback. You can do it by shunting it. It shows you how to wind the coils here. It shows you how to arrange them on the form. It gives you different methods of hooking up your apparent coils. Whenever you see an arrow through the coil, a transformer, that means the coupling is variable. It means either you're pulling the coils apart physically or rotating one with respect to the other. And it just goes on and on with different ways to control it. Here's an interesting one. You actually wind the feedback on a loop antenna. This, now you got a probe you can wander around with. And by controlling the feedback into the feedback winding, you control the regeneration. This is very good as a point source pickup. And you have all sorts of methods of showing how to make the feedback in the regeneration. Basically, this is for the technical people who want to be able to actually figure out how to make their own experiment with detectors. Of course, they show trials. There's nothing that says you can't put a tetrode or a pentode or a pentagrid tube in here and get the same results. And that's the end of that book. Now, that covers basically your amplitude detectors. As you can see, if your amplitude detector is a type that is a semiconductor or a point contact, it's basically creating a potential field inside the detector that your potential field can modulate and change and vary the output voltage of that detector. One thing I will go into here is the reason you have troubles with the grown, diffused junction type detectors. To make a PN junction, you need a P material and N material. What is that? P has a hole or an absence of electron, and N has an extra electron. How you do this is you take your crystal lattice, it's a crystalline structure, your semiconductor crystal, and you introduce into this an ionizing agent. You put maybe a sodium chloride or a arsenic atom inside the crystal lattice of the semiconductor. Of course, if you look at a crystal, it's always symmetrical. That's saying that ion can drift all around inside that crystal structure. What you're going to find, as your currents change, the position of that ion is going to change. Now, being that these etheric functions are very small waves, where the phase velocity is zero and the root velocity is instantaneous, This wave now is almost like a liquid as it goes through the crystal, and as this ion moves around, it distorts it. This is one of the reasons solid-state devices do not process the etheric domain as well as they should. Of course, you can process and place the ion in one point in the lattice by putting a very strong magnetic field. But that, I feel, it's more practical to use a vacuum tube. Okay, FM detectors. This takes a frequency shift as the frequency is moving around, frequency versus time. It converts this frequency shift to a voltage shift. You can see basically you have one network tuned at one frequency, another network tuned at another frequency. You tune one network above the carrier frequency, one network below the carrier frequency. When you're exactly in between, they will sum. You have one give you a positive voltage above, the other give you a negative voltage below. When you're right on the center frequency, you get E1. That's 0 volts. When you go up, you now start to get more positive voltage than negative voltage. You get a positive swing. As you go down, you get more negative voltage as a negative swing. That's all this is showing you here in this vector diagram. As you swing this way or this way, you're changing the DC voltage along this line and the phase angles. This is the theory behind the discriminator. You can see this is the function here, the sine and the cosine. By controlling the sine and cosine and controlling the phase angles, you can get a phase or frequency-sensitive swing. Now, you have to consider what happens if you take an FM detector and hold the frequency constant. What happens when a time stress comes through there? That time stress is going to sum in this vector diagram just like an extra component in phase. So it means the noise that comes in on an FM detector, that's time stress, that pure noise, provided the circuitry ahead of the detector can process the time stress properly. I include that because phase is time. Phase is a differential of time as the wave moves through time, moves through space. I include this for people to understand what's going on with FM detectors. And you can see you go on to tons of information on it. Huh?
What year was the discriminator circuit?
Major Armstrong in about 1935 came up with the first actual discriminator. You can also take an LC network. You have the slope. You have this slope here. Let me draw it out for you. Can everybody see this? If you look here, this is the frequency, and then this here is amplitude. If you look at the resonant mode of an LC network, it does this. Now, if you tune the network so your center frequency lies here or here, what's going to happen? In this case, as the frequency goes up, the energy is going to go down. As it goes down, the energy is going to go up. If you now take this function here and you put it through a rectifier, that's, I apologize for that. My writing is terrible. Now, when you rectify the potential here, you'll get an AM, a voltage variation, due as this frequency swings up and down the slope. This is slope detection. This is good for using RF detectors in general because this will pick up an AM wave, this will pick up an FM wave. This is what's used a lot of time in your RF sniffers. Because by just tuning off the center carrier, you can detect the FM a little bit. Okay, lights again. You can see now your detector S-curve. 10.7 in the center, 250 kc down, 250 kc up. It goes from a full negative to 0 to a full positive. This is telling you as the frequency shifts in either direction, it generates a DC potential. That's your detector action right there. This is the most important part of your detector. In this case, one side of the detector is active. In this case, the other side of the detector is active. And of course, you can go on and on with the mathematics. Let's not go on and on with the mathematics. Ratio detector is just another form of discriminator. It doesn't show the ratio diagrams in this book. RCA never did. Yeah, it shows it here. See, here's one ratio, there's the other ratio. But this is very difficult to understand unless you understand vectors. And you got different kinds of FM detectors. They just go on and on again. And then it tells you how to build the things practically. This I'm basically including for the people who would want to try to play with this. Here's all the information you need to play with it. Even gives you tube numbers, 6AL5, 6BA6. 6H6 if you want to get real old. That's that cute little short metal tube that you see in so many old receivers. And that's what this book is out of, Radiotron Designer's Handbook from 1952. This is because this one actually comes out of Sydney, Australia. You see it's published by the Wireless Press for the Amalgamated Wireless Valve Company. I don't know what PTY is, but it's very limited. But it's sold in this country by RCA.
Is it still for sale?
You gotta be kidding, Eric. I've called up RCA to see if I can get other versions of this. You see, I buy all my stuff used. This is the name of the previous owner, C. Weiss. Okay, that's the end of the slideshow. So let's turn the lights back on. Now to stress once again, you have three types of detector functions. Your power function. This is where heat or a realized power field varies some sort of a electrical potential in your circuit by measuring either resistance or the voltage generated. You can get detector action. You can get a rectification, so to say. Like a thermocouple, as you get the thing hotter, it puts out more DC. As you get the thing colder, it puts out less DC. Of course, you got all sorts of thermal legs built in that thing. And it's not at all that easy to use. A light bulb in itself is a thermal detector. If it lights, you got RF. If it doesn't light, you don't got RF. If it lights dimly, you got a little bit of RF. But of course, you'll have to string about 250 feet of wire parallel to 150 kV line to get enough detected, get enough RF to say you got something detected to light the average light bulb. Of course, in transmitters, we take a little loop of wire, put it into a neon bulb that takes virtually no power to light it, and run it up and down the transmission line looking for standing waves. That's detecting, telling you, yeah, light's brighter, you got more energy there. Light's dimmer, you got less energy there. You can also make a detector, but that's a power detector again. It means you have to have realized work to do that. Of course, since in the hyperspatial wave domain, we don't have any work. What good is that going to do? Nothing. You might as well take all those detectors and circular file them. Put it in the write-only memory. Now, when you get into a detector that generates a potential cloud, either magnetic potential or electric potential, now this is saying you got a field, no power, but potential. If you can cross the two fields, your signal coming in, you want to detect with the potential, and like in a vacuum tube or a point contact, where the size of that potential cloud controls the conductance of the tube, now you can get a rectification from the potential to the DC domain or the power domain. And then the third case is when you take a vacuum tube and you stress the darn thing to the point where the vacuum is breaking down, and you start now to generate the functions where you get F of t with respect to space. Now you got time stress waves. And that, at this point, I only know of stressing a zero-point potential of a vacuum to detect. First you build a time stress field, and by mixing that time stress field, so to say, with the incoming field, you can get detector action just as you get with the electron or the magnetic potential detector. Only difference is you're now detecting time stress. Okay, that concludes, at this point, detectors. Now I'll have questions and answers on detectors.
Are you saving this? Should I use a microphone or just?
Yeah, you do.
Okay.
That's the moment already.
The next step we'll take after this is I'm now going to go into how the 3D sound system works and what the theory is on that in the Minefield amplifier. That's going to be almost extemporaneous because I
Testing.
didn't think there was that much interest in it, so I have to do it off the top of my head. If we have time, we'll include it in the proceedings. I don't know how my time's going to go. But on detectors, you can read all the information. I also have a very nice write-up here of how the different things detect and this sort of thing, the etheric functions, which is the same thing I've just said. Okay, first question.
Yeah, you didn't take much time with neon tubes, and
That's a gas detector.
yeah, and
That generates a potential cloud, an ionized potential in the tube.
yeah,
And by either increasing or decreasing that ionization, you can have one potential coming in affect the other potential. And you can get a conductance change, and that's your detector action. That conductance will change your resistance in the detector, and by
yeah.
putting it in a circuit, you can get that detector action.
Did you encounter neon tube or low-pressure gas tubes in any of the old books that you've run across?
At the end of this, I have a few other detectors. I'm sorry, I forgot about them. I'll have to include them.
And then the second question, kind of related to that, is in 1983 when you were talking about T. Henry Morey and some of his work, Vic Hart up in Seattle, has been trying to build some of his tubes. He's always been working with low-pressure gas tubes, mixtures of noble gas.
So was Tesla?
Yes, exactly. And that's why I was particularly interested in what you might have encountered, say, since 1983 when you talked about Morey, and particularly Morey's detector for the radio, not for the power device, but for
the radio and
that
energy.
strange radio that seemed to be able to hear things without having a transmitter.
That I know nothing of. Okay. If you take a 5651 gas tube, regulator tube, that's basically an anode, a cathode, and gas. Argon, neon, krypton, that just changes the potentialization voltages. If you take this tube and you go to a very large resistor, in the 5651, by the way, this will be in the proceedings also. I have to apologize, I forgot about these detectors. When he mentioned it, I remembered, yeah, I got the information. This is about 87 volts. Let's say you put 600 here. That means this will be maybe a 500K resistor. What's going to happen now is you're going to develop a DC voltage here. This is your typical gas tube regulator circuit, except we're running the current way, 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 way down. So this thing is just barely ionized. Now, if you take and you put another power supply that's floating, the same voltage, 87 volts. Here to here is 87 volts. What you end up with here is 0. In other words, from here to here would be 0. Now, this tube has a peculiar property. If you shine light in this thing, it changes the voltage. If you put it in a magnetic field, it changes the voltage. If you have a psychic that projects well, concentrate on this thing, it changes the voltage. Thunderstorm goes over, it changes the voltage. So it means as the etheric functions, notice I use the term etheric functions as a catch-all, drifts through this tube, it's going to change the ionization potential, and you got great detector action here. Almost anything and everything will change the voltage coming out of here.
Can you hold it just a moment while I change the tape, please?
Now, what was that? I didn't catch that.
Hang on a minute.
Oh, okay. I'm sorry.
Detection using the 5651 and whether it's a potential or a time stress that
I don't know. I don't know. This is something I picked up empirically. How I found this was I had this silly little power supply sitting there that used the 5651 as a reference. And the darn thing was driving me crazy. I had psychics come through the shop. Every time they walk in, this damn power supply changed voltage on me. And I realized then, hey, we got something that detects psychic energy. Now, what in this chassis with this myriad of tubes is doing it? So we made an extension tube socket, with a long piece of wire, 50-foot piece of wire, pulled the tube out, plugged it in, took the tube over here. Here, concentrate on this. And I watched the voltage. Sure enough, I took the 5651 reference tube out of the power supply, had one of the psychics that no longer works with me on this concentrate on it, Sure enough, the thing went from 300 to 320 volts coming out of the power supply. That's the element. The pass tube didn't do it. The amplifier tube didn't do it. It was this silly little 5651, and after playing with this thing, I came up with this very nice circuit that seems to be sensitive to just about anything. You walk into a radio station with this thing, you'll see this voltage change all over the place. You'll see modulation appearing here, although it's all distorted. Because now you got the modulation as reflecting every other domain that this thing is sensitive to, all superimposing, and you're getting all sorts of Fourier transforms of the modulation being summed in on. You're getting differentiations, and the waveform that comes out of this thing for AM modulation is atrocious. But what we got here now is a thing you can put on the end of a probe. Yeah, there's something there. Yeah, there's something there. Yes, Eric?
Do the 5651s that have the radioactive material
Yeah,
thrown
they
in?
work very good.
They work good. How about OD3s or OA2s?
The sensitivity was not there. Any of the gas tubes that do it.
But the 5651 is the
radioactive
one.
doped 5651 or an OG3 from Europe
Right.
will do it very sensitive. Now, you can also take this, and in place of this, put another 5651 into a differential amplifier. The reason you want to do that is this thing is normally sitting in an etheric field. As the etheric field changes, this thing's going to drift. Now, if you reference this to another, they'll drift together. Now you got one tube sitting in a box here, sensing the overall background etherics, and now you're sitting over here walking with the probe. Now you'll see the difference from here to there. And that could be something very much like this. You just put another 5651. I'll just draw it as the tube. And you come out with your 87.5 volts. Of course, here to here it's nothing. And of course, now you have to put means to vary one voltage to the other to balance them out. When you do that, you now got a differential detector. 5651. It's one of those gas regulator tubes. They call it a voltage reference tube. Although I found those things drift more than an OA2. I'd rather use an OA2 than a 5651 because everything under the sun affects the 5651. It tells you in the tube manual to shield the tube against magnetic fields, against light, against changes in heat. Why they call it a voltage reference, it's beyond me. But that's what they call it. Now, let's hold the questions for...
The 5651 was found to have the least amount of voltage variation with respect to current variation flowing through it. That's why it was chosen as a voltage reference tube. It's a military preferred tube.
I know
Because
it's a
of that
tube.
particular function, if you have a change in power supply and the current ends up going through the reference tube, it holds a much more constant. But
Well,
they apparently
usually-
forgot about the external influences, as you're pointing out.
Yeah. What they usually do is they have an OA2 come in with your series resistor and then another series resistor to the 5651. Of course, you hold a constant voltage, you got a constant current. But that's provided everything else is taken out of the effect. And I've had power supplies that from day to day drift 4 or 5 volts at 200. And I called up RCA, like 10, 12 years ago. I said, that's the nature of the beast. Shield the thing against light. That's what they told me. I shielded the thing against light, still didn't work. But let's not go into that. That's a dead horse at this point. Let's now go into a next kind of detector. Huh? Let's hold the questions.
I hear
until
you saying
later.
you don't know for sure that detects scalars. It detects a whole lot of things.
It detects all sorts of stuff. It detects psychic energy. It detects canceled magnetic fields. And this sort of thing. All right, you've heard me talk of a orbital beam tube. What is an orbital beam tube? Very interesting, weird device. You have basically a cathode, a grid structure, like a regular tetrode vacuum tube. The only thing is, after that, they do something weird. They take the electron path and they run it in 2 circles. Let's see if I can draw this right. Yeah, it goes like this. 2 circles. And you have deflection plates here and here, and you know, all sorts of fancy little things in this silly little thing that looks like about a triple-size acorn tube. Here, they go into a secondary emission diode with the associated circuitry that goes with that. You can look that up in the fellow multiplier. Then they come off of here as one electron stream into a standard plate with your load resistor. This was initially designed to be used as a wideband amplifier because this capacitance, since this electron stream is very, very small current flow, and the electron multiplier gives you the current flow. You have extreme high impedance here and very low capacitance. This was meant to be used as like a video amplifier type thing. Now, I'm sure we all have seen the diagram in Feynman's book and Jack Dee's book and a whole host of others, where you have an electron source. It goes through almost a circular type thing with usually magnets, and then it comes together on a plate. And they're saying by moving this around, you can create interference patterns. Jack Dee has stated that this will detect a scalar wave. What do you got here? 2 electron orbits. You're going to create interference. If you take this and you deflect it so that only half of the stream is striking the plate, as the environment changes, you'll get more or less again, and you'll get a detector action just like here. By looking at the currents coming from the interference of the 2 beams, you see some very interesting noise, which is a differentiated signal coming in from hyperspace. I know this is a claim. I believe this to be true. I have not been able to absolutely prove what this is doing. I'm presenting this for people to think about. I hope somebody give me feedback on it. This is also included in there. That's the other type of detectors I played with that are not in the books. Okay, now we go into questions. Well, let them record you.
In Tom Beard's work, he mentions a scalar detector where there's an LC circuit and an intense magnetic field and all that in a Faraday cage. And I was wondering, have you had success with that, and what's your analysis of it?
I've tried one, and I couldn't get anything out of it. Problem is, if you look at the kinematics of that thing, you could not lift the magnet it would take to bend hyperspace 90 degrees to bring the signal in. You'd have to have superconducting magnets, and I don't have that kind of money. You know, that thing's highly impractical. You know, so you had permanent magnets, I don't think it'd fit in this room, the permanent magnet. Yes, Eric?
What about the use of magnetrons as detectors? The use of magnetrons as detectors.
If you look at one of the slides, there's a circuit for using magnetron as a regenerative oscillating detector.
Which book is that in? Because I have a number of those books. The Terman book?
Nah, I forgot. We'd have to go through the slides.
Okay.
It'll be in the proceedings, or we can sit and view the slides later. Yes, I think it was the Terman book, but the old one. They had 2 detectors sitting side by side. One page is a Barkhausen electron-coupled oscillator, and the other one is a split-ring, split-anode magnetron going to an LC.
Another type of detector I wanted to bring up is I did an experiment once, is I took an old brush strip chart recorder and brought the amplifier gain up to the point where it was in the regeneration, but put the dampening resistance in by putting high viscosity material in the gears of the motor, so the feedback was dampened in that regard. So it was a regenerative detector for mechanical waves in the room, because any vibration in the room would move the motor and start the feedback going. But what I used as a quench for the thing is a photocell catching scattered light off of eucalyptus trees in the wind. And when I did that, it increased the sensitivity 1,000-fold.
I'm not laughing at you. I'm laughing at what you're describing.
I know, it sounds bizarre,
yes.
But it worked.
Mm-hmm. Look, I've seen people take a philodendron and put an electrode here on the trunk and put an electrode here on the trunk and look at the voltages that come out of the electrolytic voltages that come out of the philodendron and make all sorts of wild claim. I did the same thing. It was very interesting with an oak tree. I heard all sorts of radio stations on that oak tree going directly into an audio amplifier. I heard all sorts of other strange functions that I couldn't identify, and I looked on the scope, and I didn't have a scope fast enough at that time, and